So before I start, I'm going to do a little work on the board to make sure we understand some of the mathematical stuff that I want to cover today. So sometimes we write something like this, C, N, K. How many people are familiar with this kind of notation? Combination. Yep. And so C and K basically is the combination of n objects taken k at a time. It's something very important to we're going to need. It's defined to be, anybody remember? So it's going to be n factorial divided by
K factorial.
okay, k factorial and n minus k factorial. Okay? Another way you might see this also has a different notation. Sometimes we write this using this notation. Same thing. So if you see, like, notice there's no division here. So this is n choose k, the combinatorial coefficient of n objects taking k at a time. Same thing.
Oh, choose and same thing? Okay.
They're the same thing. Unfortunately, I have two very different notations, but they mean the same thing. So this also is n factorial, k factorial, n minus k factorial. Everybody understand what factorial is, right? So first of all, what is 3 factorial? 3 times 2 times 1 go all the way down to 1. So that's going to equal to 6. 10 factorial will equal 10 times 9 factorial. Okay, and that's it. So these are so-called combinatorial coefficients. Let's say, just to give you a simple experiment, let's say what I'm going to do is I'm going to try something. I'm going to try 4 attempts to do something successful. Okay, so what am I going to try to do? I'm going to try to do 4 times. Let's say I'm going to say 4 times. You guys know what bowling is? Bowling. I take a bowling ball. I roll the bowling ball.
Goes in the gutter.
You know what it is, okay. You see me bowl before? And the most successful thing I can do is hit, there are 10 pins. If I hit all 10 pins, it's called a strike. So if I get a strike, they're going to put the pins back up. I'm going to roll again, see if I can get another strike. If I get it, fine. If I don't, then they knock them down, they put them back up. So each time I'm going to make an attempt to roll the ball at 10 pins and try to get a strike. Now let's say my probability, now I will say that so basically what is the biggest number of successes I can have?
All time.
For each throw one.
4, because I'm only going 4 times.
Okay.
Okay, so I could have 0 successes, 1, 2, 3, or 4. So therefore, the y will be a variable that will represent the number of successes I have. So y could be equal to 0, or 1, or 2, or 3, or 4. No successes, all successes, and everything in between. So we're going to look at the probability that y, the variable, let's say, is equal to 2. So we're going to look at the probability that I'm going to get 2. Now, in order to do that, I need to know what is my likelihood of getting a strike in the first place. So I'm going to say my probability, P, of getting a strike in the first place, let's say is going to be, I'm going to say 0.2. So that's pretty good, actually, if you know bowling. If you can do that, it's pretty good. So that's 2/10 or 1/5. That means out of 10 times, I can expect to get 2 on average. So 1 minus P is the probability I don't get a strike. We're typically, a lot of times we call that Q, and it's going to be 1 minus 0.2, so it's going to be 0.8. On any attempt, I'm either going to have success or failure. Okay? Now, if I have, let's say I go the first time, let's say I have a failure the first time, let's say I have a success. No, failure. Success. Okay? I want to get the probability that I get 2 successes. So that's successful, right? But in order for me to get 2 successes, then I would have to have a failure here and a failure here. Are you with me?
Yes.
Okay. So now we'll take this magical device. I think it's called a fancy abacus. And what we have is we have 0.64 times 0.2 times 0.2 is equal to 0.0256. Can somebody explain to me what this 0.0256 means? I know Scott can do it. Go ahead. No?
It's the likelihood of getting 2 successes in a row for your first 2. Or just 2 successes in a row total.
You tell us. That's okay. You can be wrong. Just do your best.
Yeah, I think it's the likelihood or the probability of getting 2 successes. Yeah, getting 2 successes.
Okay. Anybody else want to make a comment? Anybody else want to make a comment? So my first attempt, I succeed with this probability. I succeed again, I fail, and I fail. So that gives me about 2.5%. So 2.5% of the time, which by the way is not very high. I will get a strike, not get a strike, not get a strike. Okay? But what happens if I get a strike and then I miss, and then I miss again, and then I get a strike? That's a different sequence of successes and failures, but it still is part of 2 successes for y. And of course, we know since multiplication is commutative, it's going to be also 0.0256. So the question is, specifically here, how many ways can I configure these 2 2s and 2 8s to get 2 successes that are different? Okay.
4 factorial by 2 factorial into 2 factorial.
And more generally, if I try n times and I have k successes, how many of those? Because anytime I have k successes out of n attempts, however I order the successes and the failures, the product is the same. So therefore the probability must equal to this probability times the number of times these numbers can be rearranged. And so the number of times these can be rearranged, in this case, it's going to be 4, choose 2. So here we are. So here are 4. So there are 4 elements. I'm choosing 2 of them. So I can choose them to be, and these are my successes, to occur in the first 2 positions. Okay? But I can also succeed here, miss, and succeed here. That's a miss. I'm only showing the successes. I can start here, and I can succeed here. I think everyone will agree that these are the 3 ways that I can have 2 successes with me succeeding the first time. That's the only ways I can have 3 successes with a success in the first one. So that means if there are any more ways to succeed with 2 strikes, I will have to fail on the first one. So therefore, I will succeed on the second one. And of course, second and third is another way to succeed too. And another one would be 2, then miss, then make it. And that gives us 1, 2, 3, 4, 5 options. And finally, I think everybody will agree that these are all the ways that I can succeed on the second chance or the first chance. So therefore, the only remaining one is to succeed on the third and the fourth. And if you count them, so you have 1, 2, 3, 4, 5, 6. There are 6 of them, which is equal to 4 factorial over 2 factorial over 4 minus 2, which is 2 factorial. 4 factorial over 3 factorial is 4 times 3, because the 2 factorial takes away the 2 and the 1. But then you still have a 2 factorial on the bottom, which is equal to 2. So this is 12 over 2. That's equal to 6. So therefore, if this is roughly speaking, 2.5%, then 6 times that, 6 times 2.5% is going to be approximately 15%. Correct? So that means that 15% of the time, what?
You're gonna get 2 strikes.
I'm going to, from 4 tries, I will get 2 strikes. 15% of the time. What will happen 85% of the time?
Something else.
Something else. Can you tell me what could happen?
3 strikes.
3 strikes,
1
4
minute.
strikes, very likely not. Or 1 strike or 0.
Or no strike.
Okay, so the probability is 15% I will get 2. 1 minus 0.15, which is equal to 0.85. That's the probability that I do not get 2 strikes in 4 tries. It doesn't mean I'll get less, it doesn't mean I get more, it just means not 2. It could be 3 or 4, 1 or 0, which are all the possible ways. Right? All right, so any questions before we dive into hashing again? Everybody got that? Any questions? Everybody's cool on that? Like, yeah.
Can I say that probability of not
I can't hear what you're saying because I have this big motor behind me. What? Hold on a second. Yes?
There is P of y is equals to 2, which is probability of getting successes, right?
The
Can I
probability
say-
that the number of successes, y is like a variable. We're going to have some successes or how many
I
successes?
mean,
we
2
want?
successes.
Yeah, so
Right.
probability
Can I
y
say-
equal to 2 means probably they will get 2 successes.
So can I say that is the probability of getting 2 failures as well?
Well, yes, because we have 4 tries. But if we had 5, the probability of 2 successes would be the probability of having 3 failures.
Yes. In this
Absolutely.
case, we can say that it is a probability of failure as well, right?
Yes, we could, absolutely. Everybody understand what you're saying?
Yep.
Okay, then you can explain it to me. No, just kidding. Yes, absolutely true. All right, so let's take a look at our hashing thing. Let me first have to get the slides to where they're supposed to be. So I think last time we started talking about hashing with chaining. We can apply some interesting probabilities here. Okay, so I'm going to just go back to here. No, I think this never works the first time, so it's going to go back to the way it was. It's fine. About doing hashing using a technique called chaining. And chaining is a way to resolve what?
Collisions.
Collisions, okay, that's the word we're looking for. And we found out that basically the average complexity of an insertion at the back of the list, successful insertion. Okay, we can say successful insertion means that we hash to a list, we traverse the list. Hashing is free, theta 1. Traversal is going to be the length of the list. So that could be 1, but it could be n. If the list is very long, if everything goes in one list, it could be n. If everything goes in 2 lists, it's n over 2, which is still theta n. So we came up with the idea, if the number of lists is approximately equal to the number of elements that we're hashing, then we have big O of 1. The average complexity of an unsuccessful retrieval, we hash to a list, we go through every element in the list, but none of them are a match. So the hashing is free, and then there's a traversal. So we find the key, we fail to find the key in the list. Every list is equally likely to be returned from the hashing function. The analysis is the same as the insertion above. So therefore, that means that failed search gives us pretty much big O of 1 as well. Okay. Average complexity of a successful retrieval. A successful retrieval is going to be if we insert all the keys in the back of the list, then the complexity of a successful retrieval is 1 more compare than the insert. Because when we inserted it, we said, not a match, and insert. But now, successful retrieval, not a match, match. So we do 1 more comparison. So when we do a successful retrieval, we do one more comparison than the insertion. Does that make sense? Yeah? Now, interestingly enough, let's consider the jth entry into the hash table. So the jth entry means that we are now entering the jth element into the table, which means we're hashing the jth key or jth record. We're going to say the average cost of this insertion is j minus 1 over m. What does that mean? It means when you are inserting the 100th entry into the table, you can take 99 divided by the number of lists, and that's going to be the expected average length of each list. Does that make sense? So, again, so when I'm putting the jth entry in, there are already j minus 1 entries in the table. I'm dividing them by the number of lists, which is the number of possible hashing locations. And because, okay, and this explanation, so that you understand that. So therefore, the retrieval cost will be exactly the same as the insertion cost plus 1. That's what we talked about, it's 1 higher. So all I have to do is the average cost of all possible successful retrievals, the average cost of any successful retrieval is going to be a sub n, which is going to be 1 over n possible elements. Each one has the same weight, so we do 1 over n. And we're going to sum as j goes from the first element to the last element of the cost of a successful retrieval. Of course, this is going to be 1 over n is here, but it can come out in front of the summation because it's just an average. So what we have here is this comes out to 1 over mn times the sum of j minus 1 plus 1. And when we simplify all of this, we get n minus 1 over 2m plus 1. So therefore, again, if m is very close to n, then it's going to be something close to itself over 2 times itself. So it's going to be roughly a half plus 1, about 1.5 theta 1. Okay. And the last one is the successful deletion. So I'm going to skip that. I'm going to let you look at that on your own. Okay, I want to talk a little bit about hashing functions in general, and then we're going to do some analytical work. So how do you create a hashing function, first of all? What's the objective of the hashing function? Can somebody tell me what is the objective of the hashing function? So I have a hash table with n slots or n chains. What's the objective of the hashing function? Given a key goes into the hashing function, what's the objective?
To map each token with a unique ID.
We can't do that because we know that there's going to be some collisions. We want to minimize the collisions, right? So we can't talk about that type of a goal because we can't achieve that goal unless we use perfect hashing, but perfect hashing is not practical. So the goal is that when a key goes into a hashing function, we want each slot or each chain to have the same probability of being selected. We want each chain or each slot in a hash table to have the same probability of being selected. So if I have 1,000 chains, what do I want my probability to be for a chain to be selected from that one?
1 by 1,000.
1 over 1,000. Absolutely, 1/1,000th. Okay, very good. If I have 100 of them, 1 over 100. So if I know that the probability of being selected is 1 over 100, then I know the probability of not selecting a particular slot is going to be 99 over 100, which is 1 minus 1 over 100. Okay? Now, would you agree that if the probability of a particular slot or chain being the result of hashing has a probability of 1 over n, which is the number of chains or slots, that is the best we can do in terms of having our hashing function? Is that the best we can do? Is it the best we can do so that every chain or every slot in a hash table has 1 over n probability given n of them? Because if you say no, I'm going to tell you that if all of them have equal probability, you're saying that's not the best. Well, all the probabilities must add up to what?
1.
1. So if they're all equal, you don't like that, you're going to have to pull somebody's and add it to somebody else, which means you're going to make some of them bigger than others. And I'm going to prove it by contradiction. And you're going to say, oh, okay. So it is the best we can do to have the probability of any one slot in a hash table being selected to be 1 over the number of slots. With n slots, r over n. Or what did I say? 1 over n. Jumping to the next topic here. Get the camera on me. Okay, so, all right, so let's say we have 1,000 memory slots. A key is a string. So keys are typically things like strings, numbers, combinations of things. We want to have as much input into the hashing function to give the hashing function that desired goal of equally likely targeting of the slots. So, for example, let's say we want to hash the name Joseph. So we can basically say, okay, 74 is the ASCII value of J, 111 is the ASCII value of O. So if I multiply these together, I get a crazy number, 8214. And then maybe if I do a modulo of 1,000, it'll give me 214. So I'm going to put that guy in 214. Thomas is going to be 84 times 111. I'll do modulo of that, and I'll get 324. You get the idea? So notice that I'm getting different numbers for these different names. Yes?
Are there any generic hashing functions?
Well, there are many hashing. For example, if you program in Java, there is already a hashing function. There's a hash code. Every object has a hash code associated with it. So you can just say for every object hash code, and Java will give you something based upon its best guess. If you want to do a better job than that, you can override the hash code function and make your hashing function more powerful. But Java gives you a default hashing. Okay? So you can see that this looks pretty good, but there's going to be some major problems with this. As you can probably imagine, what makes a good hashing algorithm? We already said that. Why is our example before not a good hashing algorithm? Well, because Joseph is nice, but John and Joanne all have the first two characters, so they will all hash to location 214. So it means that maybe if this is the key, we're not using as much of the key as we could. Okay? And also, even if you use the whole key, Joseph, does that mean there's not going to be another Joseph? You see what I'm saying? So maybe that's not even the best idea, because again, it's probably not going to give us that probability that we're looking for, that ideal probability. How much memory should a hash table use? And when I say how much memory, we're talking about how much more. If you're talking about a hash table with slots, so you got 100 records, 100 slots. That's the minimum you can have. You can't have less than that, otherwise you can't house all the records. So typically our hash table will be having more slots than minimum. And the reason for that, we'll show the reasoning behind that mathematically with our best case assumption of 1 over n probability of targeting any one slot. We're going to just assume that's the case. So that means we cannot do any better than that, but we could do worse than that. Okay, so hashing without any collisions is practically impossible, and this crazy number, I don't even know where it comes from, but it's very unlikely that you're going to get hashing without collision. In fact, that would be a hard mathematical problem, but a good one to find the probability of no collisions. I'm not going to give it to you. It's not interesting. It's just not going to happen. I will show you statistically that if you have n slots and n records, it's going to be a disaster, even under the best assumptions. Because remember, we never know when the keys are coming in. Okay, so a good algorithm is randomizing. We want to use a good part of the record of the key. So maybe not just the first name, maybe some of the last name, maybe birth date, something, just kind of put it up. So, so I'll show you some basic ideas. So here's some hashing functions we can use. So let's say we have Joseph, we have Melvin, so you can see some ASCII values here. If we are too short, then maybe we add some blanks in here, or maybe we start using the last name. Would be another possibility, right? So one interesting idea is to do something called folding and adding. When you fold, what you do is basically take this 74 and a 111. You are actually going to add these, but not 74 plus 111. We're just going to say 74 times shifted over by 3, because this has got 3, and then add the 111. So this will be 74,011 by simply concatenating those digits. and then you get this one, and then you get this one. And then what you do is you take this, and you take this, and you add to this, and you add to this, and you get a really crazy number. Okay? And then what you do is after you do that, what you can do is you can take this number and you can do a modulo, which is remainder, over another crazy number. And typically what you want is you want this number, notice I'm repeating that number because I like it a lot, is I want this number to be a prime number. Because dividing by a prime number tends to give us less duplication of slots. It tends to distribute better. So if you have 100 slots, modulo of 100 is probably a bad idea. So you might want to say, hey, I want to have 100 slots. I have 80 records, I'm going to do 100 slots. That's going to give me 80% packing density. I'm going to say, okay, why don't you add the number of slots? Why don't you increase 100 to the next prime? What's the next prime over 100? 101. So make 101 slots, you're going to get better performance. Try it out, right? So here we divide the large prime number, which tends to produce a better distribution. So here we're taking this number, getting a better distribution. So this one gives me this. This one gives me this. This one gives me this. I add them, I get this number. I take it and I do one more modulo by this one. And then I'm in good business. Of course, I probably want to use more than just Joseph. Okay. Blah, blah, blah. So we talked about perfect hashing. Perfect hashing is only possible if you already know ahead of time what the keys are. And if you have 100 keys and there are 1 through 100, then you can have 100 slots. But if you have 100 keys and their numbers are crazy, you can't. You have to do a hashing function that will take a crazy number and put it somewhere. And that's more typical. Okay? Most keys map to unique hash slots, but some do collide. Collisions are called synonyms. That's more typical. Worst case scenario, all keys map to the same slot. That's called the worst possible hash function. It just says, okay, go to slot I all the time, all the time. Then you just, disaster. It'd be very hard to be that bad. Realistic worst is that all maps go to a subset of hash table slots. So I have 100 slots, but only 20 of them get targeted. Maybe it's a bad modulo. So again, go to prime numbers, because prime numbers are going to distribute it better. Don't do a modulo by a factor of 10 or 5. You know, do something at least an odd number, some kind of nice odd number or a prime number best. All right, so that blah 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 blah. Skipping that. Some more hashing functions. I'm just showing you things that you can do. So you can take a key, you can square the key and take out the 3 middle digits. See how clever that is? So again, you think of clever things. You can, how would a key be used? Well, you can use your birthday. How do I compute the birthday? Maybe you can compute the birthday by the number of days since January 1st, 1963. That's a unique number that you will have that somebody else probably will not have, even if their name is Joseph. Okay? Another way is to do some things using a different base. So you take the original key is 1253, convert it to base 8. So this is 5 times 1, 4 times 8, 3 times 64, 2 times 8 times 64, whatever that is, 2 times 3, 2 times... 64. So it's going to be 2, 4, 8, 64 is 2 to the 6, 2 to the 9. So 2 times 5, 12. Get the idea? And then do an octal key modulo 101, which is a prime number. Again, you get crazy number distributions. And you get all numbers. Modulo returns 0 up to 100. So you have 101 possible targets. Okay, now let's think about some of the mathematics. And there's some on some of the easy examples. I made some horrible math errors. I have to point them out to you. So don't worry about that. We'll fix them up all here. Okay, so listen very carefully. I'm going to be hashing a record. So I'm going to take a record. I'm going to put it to the hashing function. We are now going to assume the best possible scenario, and that is that the probability of a particular slot being chosen is probability of y. So probability of yes means that the slot is chosen. So I'm going to look at all the slots. I'm going to look at this slot right here. Probability that this one is chosen is going to be probability of y. Probability that this slot is not chosen means the probability that any other ones are chosen, but not this one. That's going to be probability of n. So therefore, if we assume equally likely probability and a best possible hashing function, the probability of y is 1 over n. And the probability of n is 1 minus that, which is n minus 1 over n. Right? So 1 over 100, 99 over 100. 1 over a million, 999,999 over a million. Right? Okay. So probability that 2 keys hash to a given slot is going to be probability of y times the probability of y. So I got 1 key hashes. The probability it goes here is probability of y. Probability the second one goes same place, probability of y. So that means that since they're independent, because the hashing function independently treats each key, doesn't say, okay, you went over here, so I can't. No, it doesn't think. It just, each one is equally likely. So the probability never changes. So therefore, it's 1 over n times 1 over n is 1 over n squared. If n is equal to 100, that is equal to the probability of 1 over 10 to the 4th, or 1 in 10,000. There's only 1 in 10,000 chance that given a set of 100 slots, the 2 records will go to slot this one. So I'm looking at the 100 slots, I'm looking at this one. What's the probability that these 2 records both go here? 1 in 10,000. Okay. Now here, what's the probability that one hashes to a given slot, but the second one goes to any other slot? That means one goes into the slot, the other one goes to any place but there. Well, that's going to be 1 over n, that's the yes, times the probability of no. So first one goes, second one doesn't go, and that's going to be given as 100. It's going to be probability of y times probability of no. That's going to be probability of 0.0099. So 99 hundredths of 1%. Scott?
Why is that still so low? Or so
Why is it so high?
Oh, why is it so high?
Why is it so high? And because probability of, this is 1 over, this is 0.01, this is only, right, 1/1000th left. And the reason for that is because the second probability is almost certain. The probability of no is almost certain. It's 99% certain.
Right.
So this is 99% of 1%. 99% times 1%. 99%. Now here's where I have my mathematical error. So I apologize for that immediately. It's horrible. Okay, so here, what's the probability that the first 2 keys hash and the other 2 keys do not hash? So we're going to have a yes, yes, no, no. You already remember what I had on the bottom of the board there? Aha, aha, 2 keys hash. So yes, yes, no, no. This sequence is only one of 6 sequences that can give us this result. So therefore it's going to be 1 over n squared, which is yes, yes, right? Times n minus 1 over n squared. But that only accounts for that one sequence of 2 successes, yes, yes, no, no. And if n is equal to 100, I don't know what this is. This should be probability of y squared times probability of n squared. And this number is off. So I will compute the number for you right now. It's going to be 0.01 times 0.01, right? Times 0.99 times 0.99. So our real answer, you have it? 0.1234. 4 zeros, 9801. Yes? That's what you got to?
I think.
Oh, I thought you were doing okay. I thought you were checking. I don't want to make any more mistakes. So the probability of yes squared times the probability of no squared when n is equal to 100 is equal to 0.00009801. Yes. Think about it. 0.01 squared is going to be 0.0001, right? So if I multiply by 0.99, I'm just going to reduce that 1 to a 98. So that's correct. Now, what I'm going to do, so you understand how this is working, right? So I think I have some crazy numbers up there. I don't know why I did that. Are you checking what it makes?
Yes.
Right?
Yes.
Okay. I want to be right. I don't want to lead you astray. Okay, so, and we know that there are 6 ways to do this. These are the 6 permutations. So we're going to take this number and we're going to multiply it by 6 and so this is again wrong. So the true answer should be 6 times the correct number. That's going to be 0.000588. So 0.000588. Pretty small. Pretty small. But what makes it small is those first 2 getting in there. Or any 2 getting in there. Because that's going to give you 1 over 10,000. And that's going to reduce the whole probability of 2 successes. So you're unlikely to get 2 going in the same place. Unlikely. 0? No. Unlikely. Okay. All right. Hopefully now we have no more errors. All right. So in general, if we have R keys hashing, the probability that some of them, X of them, hash to the slot is the probability of yes to the X power, that's how many of them are hashing to the slot, and no is R minus X, because we have a total of R keys. So X of them are yeses, and R minus X are no's. But that only gives us the successes followed by the failures, so we have to now multiply it by this combinatorial coefficient that we had over here, which is going to be the combination of R choose X. So R records taking X at a time, that's going to be R factorial over R minus X factorial times X factorial. So we need to multiply by this binomial coefficient. So therefore the probability that we have X successes, that means the probability that X records hash to a given slot, given that we're hashing R records, the probability that X of them will go to a slot is the combination R into X times the probability of Y to the X times the probability of no to the R minus X, which can be simplified in our case because we're using the equally likely probability assumption, which means that every slot has the probability of 1 over n. Therefore, the probability of yes is 1 over n. And the probability of no is this. So therefore, it's going to be this combination times 1 over n to the x times n minus 1 over n to the r minus x. Are you with me? Okay, so now you can understand. So this would take a little bit of work to compute. Now, I want you to notice one important thing here. So, this is very easy, we know that already. The probability that one key goes to a particular slot is 1 over n, but the probability that from R keys we have somebody hashing to that slot is R over n. That's because we have 1 over n, another 1 over n, 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 R times. R times 1 over n is R over n. That's the probability that somebody will actually hash to a particular slot. Probability, right? So, that's the probability. So, note that R over n, from this discussion we had last Monday, is also known as the packing density. Because if I have R records and I have n slots, then my packing density is R over n. The number of records over the number of slots. Remember, the R is less than or equal to n. Cannot be more than n because then you have records that don't go in. So R is at most n. But if we want the packing density to be less than 100, then we make R less than n, and we give some free space. Okay, now there is a distribution called the Poisson probability distribution, and I'll show you why the Poisson is so significant here. The Poisson probability has a closed form for P of x. What is P of x? Well, this is P of x. PRX is the same as P of x. The probability of x elements hashing to a given slot. For any slot, the probability of x elements hashing to it is equal to R over n to the x times e to the minus R over n divided by x factorial. That's the Poisson probability. And you say, well, how can I believe you? How can I believe you that you're telling us the truth? Maybe you're just making this stuff up. It looks too easy. Okay, it looks too strange. Okay, so basically, what we're going to do is, how many of you have heard of the Poisson probability distribution? Poisson. Okay, Poisson,
Maybe I forgot.
you forgot, you probably different name in China, right? Than Poisson. Actually, in China, you study in China, right? So do they a lot of times they use English, right, for the mathematics?
Yes.
Yeah, that's what I'm told. Okay, so so the idea is this R over N is usually in the Poisson distribution called lambda. It's usually called lambda, and lambda is sort of the probability. But if you look at R over N is the probability of being targeted, of any slot having somebody hashed to it, is R over N. It's the probability of a slot having a record, at least one record. It's going to be 0.6, or is it 0.6? It's going to be R over N, whatever R and N are. So this is nothing more than the packing density, but it's also the probability parameter of this one. Okay, so these are the variables. And so here I'm going to show you something, and here I did a very, very bad job again. Not a bad job, it's actually a very nice job. There's no mistakes on it, but the problem is I confused some of the letters going from one notation to another notation. The success rate of being targeted is lambda. We're going to say that equals to n over p, where n is the number of slots, okay? And p is the probability. Are you with me? Where n is the number of slots and p is the probability of being targeted. Okay, well, in the previous discussion, how many slots do we have? R. And the probability is 1 over n. So it's really R over n. So this is really lambda equals R over n. And P is the probability of what?
Of one slot being
Yeah. So P is the probability. So again, so lambda is NP. That's the number of slots times the probability will be the lambda. So that means lambda is going to equal to packing density.
Yeah.
R over N. R over N. So if you write it like this, so I'll just show it to you so that you can see it, you can refer to it, so that you know where it came from. So really, so we're going to have lambda is equal to R over N, where N is really R and P is 1 over N. This is R times 1 over N, right? So we have lambda is equal to R over N. So the probability, what's the probability? So look at it this way, is equal to R times 1 over N, right? Is this the probability? Yes? So therefore, the probability, 1 over N, is equal to lambda over R. What's R? Number of records. So that's going to be N. So that's why I apologize for that. So basically, so what we have here is, and this is of course equal to P. It's the probability. Okay, so long story short, what you're going to do to calculate any of these values, if you have to calculate them, you will use as the parameter for Poisson, you will use R over N as lambda. R over N as lambda. So now, this is the ordinary binomial distribution, right? This is the binomial distribution. So it's basically n choose k, p successes, n minus k failures. That's how we did it before. Remember how that's how we did it before with the binomial coefficient? This is going to be p of y, p of n. Probability of yes, probability of no, k successes, n minus k failures. So if you take this distribution, what we're going to do is we're going to take the limit, and I'm not going to spend too much time on this, but I certainly will explain it if you want me to. We take the limit as n goes to infinity. N goes to infinity. So we take this. This is just what this is n choose k.
Yes.
Okay, this is p to the k, and p is lambda over n. So that's p, and that's 1 minus p to the n minus k. Take the limit as n goes to infinity. So as n goes to infinity, that means our hashing table is getting bigger and bigger and bigger without bound. So what we're going to do is, if this limit can come to a closed form, we will get the continuous approximation of the discrete binomial distribution. And so the first thing you're going to find out is that this is a constant, so lambda to the k factorial. Then we have the limit of this. And then you can see the first term basically goes to 1. This is n to the k. This is k factors of n decreasing. But as n goes to infinity, this n minus 1 is almost the same as n, etc. And it's also equal to n over n minus 1 over n minus 2 over n, like this. And as n goes to infinity, all these quotients go to 1. So that first term is going to go to 1. Okay, the second term is n goes to infinity of 1 minus lambda to the n. We can rewrite this as x goes to infinity of 1 over x of x times minus lambda. This term is going to go to e to the minus lambda. The third term is going to go to 1 again. Because n goes to infinity, this is 1 minus lambda constant over infinity. This goes to 1. 1 to any power is going to be 1. So finally, with these terms going the way they are, we have this in front of the limit. And so therefore, lambda to the k and k factorial come in. And the only term that gives us anything at all is the second term. And the second term gives us, so this is lambda to the k, e to the minus lambda, k factorial. That's the Poisson distribution. We got it directly out of taking the binomial distribution to the limit of n going to infinity. So remember, in our cases, our lambda is going to be the packing density, r over n. So we could rewrite for algorithms. This is going to be r over n to the k, e to the minus r over n over k factorial. And that will be the probability. That will be the probability of x equal to a particular value. So what I've done is taking this value here, and I replace lambda with r over n for particular values of packing density. If r, number of records, and n are the same, then the packing density is
100%.
is 100, which means that we are going to have what? 1 to the k, e to the minus 1 over k factorial.
What is k again?
K in this case, k is x.
Okay.
I know I gotta change these notes so they match up. So k is equal to x. It's the number of successful targets of a particular slot. So when r over n is equal to 1, my Poisson distribution is, so this is the value where k or x is equal to 0. So therefore this is going to be lambda. Why is lambda 1? Because lambda is r over n. Lambda is r over n, r over n. So since on this page we have r over n is 1, that means r over n is 1. That means r and n are the same. Packing density is 100. So in that case, when that happens, this is e to the minus 1 and 1 to the k. And k is the number of successes, meaning hashing to that slot. So probability that k is 0 or x is 0 is lambda to the x, e to the minus lambda over x factorial. So what that tells us is that when, now remember our assumptions are p is 1 over n. Our assumptions is that probability is 1 over n. So therefore, this tells us that even using the best possible assumptions and the best possible hashing function with unknown keys, the probability of zero records hashing to a particular slot is about 37%. 0 records hashing to a particular slot is 37%. What does it mean? It means that every slot has a probability of 0 being 37%. That means, on average, 37% of the slots will have 0 records hashed to them. So therefore, if we have 1,000 slots, suppose that n is 1,000, we have 1,000 slots, you can expect 368 of those slots to have 0 records hashed to them, which is unbelievable. We can expect, now, again, lambda is always going to be r over n, so it's going to be lambda to the x, e to the minus lambda over x factorial, lambda to the x, e to the minus lambda over x factorial, lambda to the x times e to the minus 1 over x factorial. So all of these values I've cranked out. You can see that this value actually happens to be the same one. This is a little bit smaller, smaller, smaller. They really get smaller. If I add up all the probabilities, they are going to approximately be going to 1. But the probability of 6, 7, 8, 9, 10 are going to be so small, very, very unlikely. We can sort of ignore them. They're going to be sort of the outliers. They're unlikely things. So therefore, we can expect 37% of the slots to have exactly one record hashed to them. So 37% of the records of the slots will have no collisions. They will have a single record. But 18.4% of the records will have two records hashed to them, which means the first one that goes in will be fine, but the second one will collide. 6.1% of the records will have three, which means that one will succeed, but two will collide into the same slot. Here, 1.5% of the slots will have one record succeed and three collide. 0.3% will have one succeed, four collide. Get the idea? So what we're finding here is that where are those records going to go? Well, if you think about it, what will be, so this is a trick question, but it's not a hard question. What will be the packing density after I hash all, what will be the packing density percentage after I hash all the records here?
Like 36, 70 change something.
100%. Now, why is it a trick question? Because you'd expect to take away this one. But you don't take it away because all the records are going to end up in the table. So ultimately, you'll pack them. They're just not going to all go. So some of the slots that didn't get targeted, they're going to get linear probed, quadratic probed, something like this, right? Get the idea? So this is going to be a mess. We can try to guess the number of collisions, but it's not exactly a science. It's more of a guess. And the reason for that is the following. What is the probability? Let's use n equals to 1,000. What is the probability that 368 records, which are hashing to exactly one slot, will be the first 368 records, randomly chosen out of 1,000? What do you think is the probability of that? Would you bet any money on that at all? I have 1,000 records. I'm going to mix them up all over the place. 368 of them will hash to exactly one slot. Okay? How many records will hash to two slots? How many records will hash to two slots? Or how many slots will have two records hashed to them? Put it that way. The answer is 368. And how many slots will have three records hashed to them? 183. You follow that? No. All right. What is this percentage? This is the probability that a slot will have one record hashed to it. This is the probability that a slot will have two records hashed to it. So 184 slots will have two records hashed to them. So for those 184 slots, we need to have twice that many records. So 364 records will be hashing so out of those 368 records, there will be pairs of them which go to the same one slot. And they will target 184 slots with 368 records. Okay? 61 slots will have three records hashed to them. So take 61 slots. Each of them will have three records hashed to them. So for 61 times 3 is 183. So 183 records will be hashing to slots that have that will have 3 in total. You understand what I'm saying? So if you add up all those, so 368 plus 368 plus 183 plus how many? 60 plus
15.
15. If you add them up together, you're going to get what? You should get close to 1,000. You'll probably get 999. You'll get 999, not 0.999. Because now we're talking about records. So there are 1,000 records coming in. I'm going to mix them up. 368 of them are going into one slot and one slot only. So those slots are expecting only one record hashed to them. What's the probability that those 368 will be the very first 368 records out of 1,000?
360 over 100.
The answer is, you can't say 0, but if you could, I would say 0. It's not going to happen. You're telling me out of 1,000 pieces of paper, I'm going to and I have 1,000 pieces of paper. 368 are yellow, 368 are red, 183 are blue, 60 are green, and 15 are black. You're telling me I'm going to take out 368 and they're going to be the yellow ones? Really? Because I can show you the probability of that. I don't know if we have enough zeros around this room, on the walls, to put that probability. But it ain't going to happen. Could it happen? Yes, everything can happen. Okay? My phone could vaporize. All the molecules could just fall apart at any moment in time. It could. I just wouldn't bet on it. So, the answer is, there's no question that some records will hash exactly one slot, but then there will be some of those colliders coming in. So if I take one, so how many records are hashing to 2?
184.
368. Because double this. So let's take the first one, and then if the second one comes in, where's it going to go if it collides? It's going to go basically to one of these empty slots that has nothing is colliding to it. Because nothing is colliding to it. So these slots will be waiting for bad ones. Is it possible that a record that was supposed to go exactly into one slot will collide?
Yes.
Yes. Can you tell me why that would happen?
It could be possibility like a previous record was supposed to be there and
Let's say a key goes into here, and then we have a collider. And the collider says, you can't go here. I'm going to go to the next one. But the next one happens to be the slot, which is only going to get one record. So now the record that's not supposed to collide at all, because this slot is only expecting one to target it, but it's already got one for resolution, linear probing resolution or quadratic probing. Therefore, this one is going to collide too, even though it's not meant to collide. So depending upon the sequence of insertions, we don't know how many are actually going to collide. We are pretty much guaranteed of a minimum number if you add 0 plus 184 plus 122 plus 45 plus 12. Those are guaranteed to collide. Do you understand why? So these are not guaranteed to collide. They may be good, but chances are some will collide, but we're going to say they're not going to collide. But here, the first 184 will not collide, but because there are 2 of them for each slot, 184 will collide.
There may be a chance of first 184 also collide.
Yes. There's a chance everything might collide. Unfortunately. So, but the chances are very, very low. Okay, so you understand the idea of what we're doing here? Very interesting problem, right? Very interesting problem. Now, so what can we do to improve? You can fill this up. Okay. Oh, he's a great catcher. All right, so what can we do so that we don't have... So basically, if I asked you to compute the number of collisions, you could do something like this. It's a probability is 36.8. Then with 500 slots. Okay? This is an example. What is the packing density here?
100%.
Same. Because R over N is equal to 1. Now what I'm doing here is I'm taking probability of 0. This is probability of 0, right? This is N. So what are these records?
1840 will have Z or will have nothing.
We don't anticipate collisions.
Okay.
Now we take these will have nothing going to them. Here we have 1840. These are records that are expecting to get a single. Thank you so much. Thank you. Okay, so what we have here is 1,840 slots will get nothing going to them directly. 1,840 slots and 1,840 records will go into exactly one slot. Now, we're going to say probability of 2 times n, we're going to have 920 slots. We'll have 2 records going to them. So that means how many colliding records are we going to have? 920. Because these are slots. These are slots. And how many are we going to have here? 610. 2 out of the 3 are going to collide. 225 and 60. All right. Now, what we're going to do is we're going to reduce the packing density. Whoops, no we're not. Yes we are, okay. So to reduce the packing density, R over N goes under 100%. So what happens is our Poisson distribution is going to be, so here we're going to have lambda is going to be 40%. That's packing density is lambda. So it's going to be 0.4 to the x e to the minus lambda, 0.4, over x factorial. Crank them all out. So now as we do that, if you look at the probability of 0, notice the probability of 0 is hugely bigger. This tells me, now how many slots do we have? Well, we don't know that, do we? But, can you tell me if I have R records, how many slots are there? So R over N, right? R divided by N is equal to 40%. 0.40 over 1. Okay? So N is equal to R over 0.40. 4.40 is 4/10, 2/5. Dividing by 2/5, multiplying by 5 over 2. So N is equal to 5 over 2R. Are you with me?
Yes.
So tell me now how many slots are there relative to the number of records? 2.5. That means if I have 1,000 records, how many slots? 2,500 slots. You understand? Okay, so if I have 1,000 records, then I will have 2,500 slots. That will give me 40% packing density. Now, 67% of those slots will never get targeted at all. That's 2/3. 2/3 of the slot are not going to be targeted. So that gives you a little room for some collisions and things like that. But if you look over here, notice that the probability of one record hashing to a slot is 26%. But that doesn't mean that 26% of the records will have one slot to it. Because it's 26% of all the slots. So it's 26% times 5 over 2. Oh. You get the idea? Because this is the number of slots. But the number of slots is 2.5 times the number of records. So the number of slots. This is 26% of the slots, but the number of slots is 5/2 R. 2.5 times R. So this was much better. Okay. So 3/4 of our records will now go directly into a particular slot without any competition. In the previous example, 3/4, we had only about 1/3 of them. Now we have almost 3/4 of them going to a particular, that's hugely better. Now, the good thing about this is that this is a very, very, very nice result. You can see that the probability of 2 is only 5%, of 3 is only 7/10. You see what I'm saying? It's dropping off like crazy. But the bad news is that a packing density of 40 is very expensive. Because if, for example, your data requires 10 gigabytes of storage, then you need to have 25 gigabytes of storage to implement this nice behavior. If your data needs 100 megabytes of storage, you need 1/4 gigabyte, 250 megabytes, to make this nice behavior. So in reality, 40% packing density is a little bit, it's nice, but it's expensive and we can't afford it. So it's usually, what we try to do is we try to make our packing density of 100, and here's, let's say, 40. What we try to do is basically do something like this. As we increase this bottom hand, we're increasing collisions. As we decrease the top hand, we're decreasing collision. So we're looking at a point where, see, here's the thing. If you could look at a function, I should really do that sometime. If you could look at a function where you have 40% density, or packing density, and let's say 100% density. And let's say we could graph the number of collisions here, anticipated collisions. Here, the number is going to be very, very high. But as we drop the packing density, it will be a precipitous drop in the collisions down to 40. But as we go from 40 to 30, the drop is going to be much more smaller, much smaller drop. So as we go from 40 to 30, it's better. But now, divide by 3/10. So now your data size for 1 gig is going to be 3 1/3 gigs. You see what I'm saying? See what the problem is? And if we go from 30 to 20, less collisions, but I had very few collisions here. So now I have a little bit less, but not that many less. See, I'm willing to pay $100 for some nice product. And I'm willing to pay $200 for a great product. But am I willing to pay $300 for a product that's a tiny bit better than the great one, but it's pretty much the same? Just got a couple of nice things that I don't know how I'm going to use. The answer is probably not. Why? And am I going to pay $400 for a product that's just one tiny better? It's like, no. Bad product, 100. Great product, 200. I'm going for that one. Superior product, but not really that much better than this one, 300. How much do you want to spend for it? So the idea is that you want to find a point where the number of collisions is low enough, and the memory waste is high enough. Yeah.
Professor, then are you implying that P of 0 is actually the extra space, like in terms of memory, if you say, that is the extra memory that will be needed?
Say again?
Like then P of 0 is the extra memory that would be needed when we are doing this hashing function?
Well, not exactly. No, because so let me, before I answer your question, so after I take all the records and I hash them into this hash table, what will be the packing density of this hash table?
Almost 100.
40%. 60% of the spaces will never be used, ever. Why? Because our packing density is 40%. Okay, that's the wastage, right? That's the 5/2. I don't know if that answers your question or not.
But like you said, when we reduce the packing density, we'll be needing more space.
Yes?
So, but you're saying like 60% of the space is wasted over there. So how we are going to need?
Not 60% is wasted. Well, yes, 60% is wasted.
Yeah.
Not 67, right? Not 67 though, right?
So how you're saying like we are going to need more space over there? It's going to be.
So we're wasting 60% of the space, absolutely. But what we're getting for that is we're getting, let's take a look at this over here. So let's say, let's just look at one short example. We have 10 minutes, 5 minutes
particular
left?
sweet spot, like where, like.
Yes, so that's a good question. So Scott says, is there one particular number, packing density, that people target? And the answer is, it is a trade-off. It is a trade-off. It's always better here in terms of collisions, but it's always better here in terms of memory usage. So you're willing to lower the memory usage and increase the collisions, and this is sort of the sweet spot, the optimization. We could write an optimization equation. It would be very interesting if we had an idea of what we wanted to optimize. We can absolutely optimize it. Generally speaking, and that's a good question, is people try to make the packing density around the area typically 60 to 80%. 60 to 80% is a sweet spot. If you can afford a little bit more memory, you might pull it down to 60. And the reason is because once you go below 60, your benefits of collisions are only improving slightly. It's like this. Forget about my product. If you buy a car, let's say you want to go fast. So you buy a car, and it costs $10,000 to buy a car. Very nice car. It goes 50 miles an hour. Okay, then they have another car, $20,000. It goes 100 miles an hour. But Ronaldo, he wants to go very fast. So he buys, for $30,000, a car goes 102 miles an hour. Just because he can say, I can go faster than you. So he gets a small benefit. It is faster, but the cost is substantial. So let's say n is equal to, let's make something realistic and see if we can come up with something. Let's say, not n, but r. So r is equal to, let's say, 10,000. Okay? R is equal to 10,000. So for this packing density, n is equal to 5 over 2 times 10,000. That's going to be what? 25,000, right?
Yes.
So now, what we're going to have, so so that's n. That's n. So now, I'm going to take the number, which is 0.268, and I'm going to multiply it by 25,000. And I get 6,700. So, 60, interesting, right? Interesting number. 67%, 6,700 out of the 10,000 records will go to exactly one place. Almost, so 67%. What about these guys right here? That's going to be 0.053. We're going to multiply it by 25,000. So I have 1325. 1325 records will go to exactly one slot, but 1325 will collide. Okay? So I will have a guaranteed 1325 collisions, which, by the way, is a guaranteed 13%. Now, let's add these numbers together. This is 2,650, 2,650, and this is 6,700. So we have 0, 5, 3. Look at this. So 93.5% of the records are either going to have a single collision or no collisions at all anticipated. Get the idea? Let's do one more. So that's going to be 0.007, right? Is a good one. So 0.007 times 25,000. So we get 175 records, which will go right in. But then I'm going to have 350 records, right? Which are going to be colliding twice. So if I add these together, this is going to be 400, 525. If I add 525 here, I have 9, 8, 7, 5. That tells me that realistically speaking, almost 99% of the records are going to have 2 collisions, 1 collisions, or no collisions anticipated. But really, the records that are going to be colliding are going to be this and this. These records are not anticipated to collide. So if you look at this one, because these are not going to be colliding, so if I add those records together, I will get 6,700. I will add to it 1,325. I'll add to it 175. I have 8,200 records. Those records, which are the single ones, or the first of the 2, or the first of the 3, will have no collisions on the first records. A collision, so that means we have 82% of records that are going to go in easily. Get the idea? Okay, any questions? Okay. See, I think we're working on a homework assignment for you to get you busy. Some people